Hello, my name is Joseph Carroll, and I am here in University College Cork in Professor Seamus Davis's research group, where we study unconventional superconductivity, typically through scanning tunneling microscopy, or STM. And today I'd like to talk about the detection of a pair density wave state in uranium ditelluride. Now, uranium ditelluride is a fairly new compound. Its superconductivity was only really discovered in 2019, but since then an awful lot of work has been carried out and can be seen in the literature in attempts to understand the gap structure. And so far, it seems that uranium ditelluride is a chiral spin triplet superconductor, which would be incredibly unusual. And there are only a few tentative examples of this so far in nature, the most confirmed of which is helium-3, superfluid helium-3. Now, there is a good degree of evidence for this kind of unusual state. Uranium ditelluride is a large anisotropic upper critical field, suggesting spin triplet superconductivity. Night shift data and specific heat data suggest that it is a point node structure. And STM data from Professor Madhavan's group in the University of Illinois suggests that there is some kind of chiral surface state, which is understood and predicted to be on the surface of a chiral superconductor. Now, for our own studies, we first have to discuss the structure of the plane in which we are observing uranium ditelluride and its features. Uranium ditelluride has an orthorhombic crystal structure with only one easy cleave plane indicated here in gray. That's the 0-11 cleave plane. When exposed at this plane, we see a structure like this, where we have tellurium atoms labeled here in blue with uranium atoms here in red. And here is just an example topograph that we get at the surface, where we can clearly see these two tellurium atoms. The uranium atom is at a lower depth, so is not seen in our own topography. Furthermore, here's a Fourier transform of that topograph, where we see these reciprocal lattice vectors labeled here in orange dashed circles. Now, Professor Madhavan's group in the University of Illinois report a charge density wave in uranium ditelluride. So this is one of the first things that we searched for as well. And to do this, we carried out differential conductance maps. We have an example here at 10 millivolts, and we clearly see the charge density waves here in blue dashed circles labeled Q1 through to Q3. And below, we have an inverse Fourier filtered image of that charge density wave in real space, where we can see the modulations. Furthermore, we decided to hunt for a pair density wave state in uranium ditelluride, but to do this was not particularly easy or clear. Uranium ditelluride is a very large residual density state, so spectroscopic imaging is with a normal non-superconducting tip is very, very difficult because the gap is very hard to distinguish from the background. Instead, we used a niobium tip, a superconducting niobium tip, to enhance the energy resolution and signal to noise so that these coherence peaks in uranium ditelluride could be more clearly seen. And using this superconducting tip, we were able to see variations in this superconducting gap associated with variations of the gap of uranium ditelluride. So first we measured the positive coherence peak, then the negative coherence peak, and then we were able to see overall variations in the superconducting gap. The Fourier transform of this map reveals 3 peaks at the same wave vector as the CDW peaks, but we label these P1 through to P3, representing the PDW in this material. Now, comparing these two states, the CDW and the PDW, we have inverse Fourier filtered images here, the PDW on the left, the CDW on the right, and they've looked very, very similar. However, there is a high phase shift between these two. Studying the phase at any given location in these maps reveals a very, very clear pi phase shift over the FOV. Furthermore, we find along example line cuts that these two phenomena, these two density waves, are most definitely shifted by pi. If you'd like to read more on our study of the pair density wave in uranium ditelluride, please go to our archive link, or also if you have any questions, please feel free to contact Professor Davis or myself. Thank you.